In this video, we're going to take a look at double displacement reactions that produce a precipitate rather than producing a gas. So remember, a precipitate is a solid that's produced by a chemical reaction. So here we can see two solutions. This is a solution over here and a solution over here. And when you mix them together, you see this cloudy yellow substance that forms. This is actually a solid that forms. So in these solutions, you basically have dissolved ions. And when they react, they form a compound that no longer dissolves in water as easily, and so it comes out of the solution. It precipitates out. And then eventually, if you let this settle, you'd see it at the bottom of the beaker within the water, kind of like sand at the bottom of the water. And so there's a really great demo you can watch here that highlights that, which is quite awesome. So make sure you take a look at that so you understand what a precipitate looks like when you're seeing it in the lab setting. So before we actually go and do some of these reactions, one thing you'll have to know how to figure out is if you have a solid or something dissolved. So this is where we can go and take a look if our compounds are solid or aqueous. Are they precipitating, solid, that's what that means, or are they aqueous, still dissolved? And so there's a couple ways you can do that. You can read these tables here. This is a solubility table with some solubility guidelines. And so let's say you have a compound like KCl. You find your cation first. Here's K+, and you find your anion. Here's Cl-. Both are in agreement. The K+ ions are typically soluble, and so are the Cl- ions. But what matters is the one that's higher up on top, so K+, it would call the shots. So for example, the K+ type compounds are generally soluble. So is Cl-, so it's not really a fight here. This is going to be a soluble compound. It's going to be dissolved, so it'll be aqueous. But let's take a look at something like, and since it's aqueous, we put AQ. Let's take a look at something like AgCl. So AgCl is over here. Notice silver compounds are often insoluble. But let's find Cl to see where it is. Okay, Cl compounds are soluble. So who wins? Silver is insoluble in a compound, and chloride is soluble in compounds. So the one that wins is the one that's higher up, that calls the shots. So the silver is going to make this compound overall insoluble, and so we put solid. This is something that could come out as a precipitate. You can pause the video and try the next two, and I'll take them up. So calcium carbonate. Let's find calcium. Calcium's over here, insoluble. Where's carbonate? Carbonate is over here, also insoluble. Since they're both insoluble in their compounds, there's no fight there. This will definitely be insoluble. S for solid. Let's look at calcium hydroxide. Here's calcium, insoluble. Hydroxide, up here, insoluble. They're both insoluble, no arguments there. So that'll be solid as well. We'd put S. So if something is soluble, you put AQ because it's dissolved in water. If it's insoluble, you put solid, S, because it comes out as a precipitate. And so these are the examples we did together, but there are other tables that you can use, and I'll show you one more example of a table that you can use to figure that out. So let's go ahead and do that. Take a look at a table in our set of notes here. So this was our table that we looked at earlier. The solubility tables can be found in the data tables over here. So you have those included. There's actually two solubility tables you'll find. You'll find this one over here and this one over here. And you can use whichever one you feel most comfortable using. So again, if we were looking at KCl, K is over here and Cl is over here, but they're both soluble, so they both agree with that. So this is going to be an aqueous compound in solution. And you can also use this chart over here to do it. So what you do is you'd find your potassium and you'd find your chloride. Right here, you'd match them up basically. And you'd see it says aqueous there. So chloride, potassium, match them up, aqueous. Silver chloride. So silver's over here, says it's insoluble. Chloride's over here, says it's soluble. Who wins? The one that's higher up. So this is going to be insoluble. I believe we can do that here if we just find silver. So here's silver, mashed up with chlorine. Notice there's an S there. That means solid. It's a precipitate. It does not dissolve readily in water because the ions are just too attracted to each other to be broken apart. Let's take a look at calcium carbonate again. So calcium is over here, insoluble. Carbonate's over here, also insoluble. So this would be solid. So calcium, and then we'd have to find carbonate if it's listed on here. You don't see carbonate list. Oh, here it is. Yes. So calcium, carbonate, solid there. And so it's not soluble. Calcium hydroxide. So same idea. We can do the same thing on this list here. So Here's calcium, there's hydroxide, solid, right? Or you can look here, calcium's insoluble, hydroxide is insoluble as well, so solid. Let's try the next ones here. So a very cool trick or tip that might help you just to speed things along is that generally when you see nitrates, for the most part, they're soluble. And you can see that because if you look at our solubility rules, which scientists came up with here, nitrates are at the very top and they're generally soluble. So let's just take a look though if that's true. We'll find copper first, if copper is on our list. So here's copper 2 right here, and nitrates up here. They're both soluble. They both agree with each other. So that's going to be AQ. And then we have copper 2 over here and nitrate. So here's copper 2. And then we go find nitrate, which is over here. Aqueous, also soluble. Then we go look for sodium hydroxide. So here's sodium. Here's hydroxide. The hydroxide part, if it had to say, it would say, let's be insoluble. But sodium says, let's be soluble. So who wins? Who's higher up? Sodium's higher up, so it's going to win by saying that it's soluble, so we'll put AQ. You can take a look at that over here. Oh, it's a bit off the screen here, but we have sodium at the bottom there. And then we go to hydroxide, which is over here, and that is AQ. So you can use any one of these solubility tables. You can take a look at where to find them here. So if you go to our handout, you click on the solubility table link here. You can find it in other data tables right here. And so you can see the solubility guidelines over here in both those charts there, and you can choose whichever one you want to use. If you notice that there's something not included in the chart over here, you might want to use a chart over here. You can just go back and forth between them. So let's go ahead and do some practice problems with these type of reactions where you might have a precipitate form. So when you have a double displacement reaction, in general, if both your compounds are aqueous, you would actually say no reaction. And the reason that is because the ions are still swimming around as they were before. They didn't form anything new. So if they both end up being aqueous, we say there's no reaction, unless, of course, it's a neutralization, which we'll see in the next video, or gas formation. So for example, up here, notice how when we first did double displacement, they were both aqueous. So you might say, oh, there's no reaction there because the ions didn't really move around or change that much. But because this one decomposed, it made a gas, so there was an actual reaction that happens. But sometimes you'll get a reaction where you have both products are aqueous, and in reality that means nothing happened. So let's take a look at that. So here we have a couple examples. We have CaCl2 plus KClO3. We're going to do a double displacement. So we're going to switch, the cations will switch spots, and we'll get KCl plus then CaClO3 2. And we need to find if these are soluble or insoluble in solution. So I'm going to go find KCl first. KCl, K's up here for soluble, and Cl is over here for soluble as well. So K, that's aqueous. So that's going to be aqueous there. Perfect. Okay. So the ions in solution swimming around are the K plus and the Cl minus. But now we have to look for calcium chlorate. Calcium chlorate. So let me just erase a few things here. Let's go find calcium first. So calcium's down here. If it had it say, it would be insoluble in a compound, but chlorate's over here. Chlorate's higher up and wants to be soluble. So chlorate calls the shots, and so that means this is soluble. This is aqueous. And so because we have both of these, let me just double check that. Yeah, that's right. Both of these decided to be soluble. Here we would say that there's no reaction. So therefore, no reaction, NR. And again, that's because the K plus, all these were all in ion form. They were all swimming around in water. They weren't committed to one or the other. They were just swimming around. K plus was swimming there. Ca plus was 2 plus was swimming there. Cl minus swimming somewhere else. ClO3 minus swimming somewhere else as well. And then we say they switch spots, but they didn't form anything new. They didn't form a new solid. No one is really committed to each other at the moment. So they're all still swimming around without forming anything new. And we also, since we don't see that there's a gas forming, since we don't see one of these special compounds here, and also we don't see that it's a neutralization, like we don't see an acid and a base reacting, we say that this is no reaction if they're both aqueous. let's take a look at another example of this, just to see what that means. So we're going to go ahead and do this reaction where K will switch spots with lead. And notice that the lead is 2 here. So it's going to be PbI2 with our crisscross, and then potassium nitrate with our crisscross. Remember that nitrates are typically soluble, so AQ, but we'll double check in our table over here. So we have nitrate at the top here, and potassium is at the top too, so they're both soluble. So that's fine. We're going to put soluble for that one. But we have to look at lead 2 iodide now. Lead 2 iodide. That's where it gets a bit tricky. We have to figure out what we're dealing with. Are we dealing with something insoluble or soluble? So lead is over here, lead 2, insoluble. Iodide is over here, soluble. So who's going to call the shots? Lead will call the shots. Lead will decide who wins. So lead, because it's higher up, is going to make that compound insoluble, a solid. So this here is a precipitate. This is a precipitate that formed, and so that means that we have a reaction that happened. This is actually the yellow precipitate you saw in the previous picture with the demonstration there. So we have a reaction that happens because we have a precipitate. Let's take a look at the next one. So the next one you'll notice it's not acid-base because there's no, any acid present with the H in the front, and I don't see any bases there, no carbonates or OH minus. So we're going to try to see if we have a precipitate reaction happen or a gas reaction happen. So they're both aqueous to start off generally, and what we're going to do is we're going to make the cation switch spots, and so the K will become KCl with Cl there. And we saw above here that it's aqueous because we already figured that out. And then we're going to have barium sulfate, so crisscross between barium and sulfate, and that gives us BaSO4. And so we have to take a look if that is classified as soluble or insoluble. So let's find barium on here. Barium's over here, and sulfate, where is that? Sulfate's over here. So we have a disagreement. Barium would want insoluble, sulfate would want soluble. Who wins the disagreement? Well, barium does because it's higher up. It's guideline number 4 higher up than guideline number 5. So it calls a shot, so our compound there is going to be insoluble. It doesn't dissolve, and it's going to come out as a precipitate. So that means there's actually a reaction that happened in this double displacement reaction here. So let's try one more example here. We're going to write a balanced equation for the reaction of copper nitrate with sodium hydroxide. Include the appropriate subscripts. So generally, when you do a double displacement reaction, your reactants start out as aqueous. But let's just take a look to make sure we're on the right track. We're going to write these out as copper. By the way, I didn't balance all these up here, so you'd have to go back and check for balancing. So copper 2 nitrate is CuNO3 2, and nitrates are typically soluble. And it's reacting with sodium hydroxide. And using your solubility table, you can go and take a look at sodium hydroxide. So sodium is up here, hydroxide is down here. Sodium calls the shots of being soluble, so aqueous. And now we're going to do our double displacement. So we're going to switch cations there with each other. And so we'll get NaNO3, and that's still aqueous because it's a nitrate, plus copper 2 hydroxide, so CuOH2. And we need to figure out if this is aqueous or not, because I don't think we have a acid-base reaction happening here, and I don't think there'll be a gas forming either. We don't have one of those special compounds that's forming. So we have to see if this is solid or not. If it's not solid, it'll be no reaction, but if it's solid, there will be a reaction. So copper hydroxide, copper 2 is over here as soluble. Hydroxide is over here as insoluble. So hydroxide calls the shots. This is our solid over here. This is a precipitate that has formed. And so that means there was a reaction overall. So far in the last video, we've seen double displacement reactions that produce a gas with one of these special compounds over here. But sometimes you won't have one of these special compounds produced, and so you'll have to see if your double displacement reaction produces a solid. So if you notice that both of your substances are aqueous, and it's not one of these special compounds over here that forms, then you're going to write no reaction because the ions haven't committed to anything. They just keep swimming around. But if you have a solid that forms using your solubility guidelines, then you have a reaction. So these ones come out of the solution and become a solid, and these ones stay swimming around in the solution as is. In the next video, we're going to finish off double displacement reactions by taking a look at the neutralization reactions more specifically.